Thank you all for joining. This is an interview about the Flink Kubernetes Operator that has been launched earlier this year. And I'm very excited to have two of the main contributors of the project here today. One is Gyula, he's a PMC member at the Apache Flink project, and Mátyás, who is a regular contributor to Apache Flink. And yeah, I would like to ask both of you to quickly introduce yourself to our audience.
Right. Thank you, Robert, for the invitation. We're very happy to be here and discuss this new project. So my name is Gyula Fóra. I'm a software engineer working on Flink. I've been working on Flink since the very early days of the project, mostly working on Flink streaming, and in recent years and months, I shifted my focus more towards enterprise integration and quite recently to the Flink Kubernetes Operator.
Hi, thanks for having us, Robert. My name is Mátyás Örhidi, and I've been in the IT industry for almost 2 decades now, wearing different hats, working in different positions. I've been a developer, like solutions architect, tech lead, even a manager. But my current title is, I guess, software engineer, and I spend most of my time these days working with Flink. I've been working with open source big data technologies since 2016, and in the last few years I've been focusing on distributed stream processing, and together with Gyula we are actively working on the Apache Flink Kubernetes Operator.
Great, thanks a lot. So I would also like to quickly introduce myself. My name is Robert Metzger. I'm a committer and PMC member at the Flink project, also since the very early days. So I know Gyula for a very long time already. And I'm currently working at Decodable as a software engineer on the Flink service at Decodable. So let's start talking about the Kubernetes operator. And my first question is about your motivation to kick off the project. So why did you build something new instead of using some of the existing Flink Kubernetes operators that already exist?
Yeah, so before I answer this question, maybe we can just take a small step back and discuss what is even a Flink Kubernetes operator. What is a Kubernetes operator? Mm-hmm. So Flink itself supports running clusters and applications on Kubernetes in the cloud. But when you do this, you have to run your application. You need to set up your cluster infrastructure manually, or you can use the Flink native Kubernetes integration to submit jobs directly. But it's a quite manual process. What operators give us is basically an abstraction layer on top of Flink, which that kind of allows us to declare jobs and clusters in a high-level specification, and the operator will take care of managing this for us without having to interact with Flink or Kubernetes directly. So this is the operator, and for companies who are running Flink on the cloud in production, this is very valuable. It kind of removes a lot of operational burden from them. So naturally, there have been a few operators developed in the open source world, and up to this point, before the Kubernetes operator project, we didn't have any operators as part of Apache Flink. So Apache Flink's responsibilities ended at the manual cluster submission point. So this is kind of the background of operators for Flink. And on the other side of this, if you follow the Flink user mailing lists and dev lists, there is a constant stream of questions that kind of tie into like Flink operations in the cloud and on Kubernetes and operators. So there was a clear need from the community to have an operator that is officially part of Flink. It's maintained with Flink and is developed constantly. As the Flink features develop, the operator should kind of follow it and also improve. Yeah, so this is why we decided that it would be great to start the Kubernetes Operator project. We had a Flink improvement proposal. It was, I would say, very successful in the community, and there were a lot of initial traction and interest in this project. So we started building the first version of this, I think, back in February, and that's when the project started.
Cool, thank you. So maybe it's actually a good question you brought up. What is a Kubernetes operator? So can you describe what a Kubernetes operator is from Kubernetes perspective? Like, where does it run? How do you interact with it? What does it do? Not specifically the Flink operator, but Kubernetes operators in general.
Yeah, so in Kubernetes manages different types of resources in the cloud. So Kubernetes comes with a set of built-in resources like deployments, pods, services that are part of the Kubernetes ecosystem, and everybody who has used Kubernetes are probably familiar with these. What the operator allows us is to define new types of resources that Kubernetes will understand, and the operator will manage them for us as if they were part of the native Kubernetes ecosystem. These new resources are called custom resources, because they're not part of what comes by default from Kubernetes. In our case, the new custom resource that we introduced are Flink deployments, which represent like either cluster or application deployments of Flink on Kubernetes. And the operator is basically just a process running on the Kubernetes cluster itself, which will watch these new types of resources as they are created and modified by the user, and it will execute actions on behalf of the user to manage these resources. So just to give like a very simple example, you define your Flink deployment in a YAML where you describe your Flink base image that you want to use in your cluster, and like cluster configuration and maybe job arguments for an application. You simply submit this Flink deployment YAML to Kubernetes. And since now we have an operator running, Kubernetes will understand that this is a Flink cluster resource, and the operator knows how to turn this YAML into an actual running Flink cluster and manage it for us.
Yeah, it's basically, in a nutshell, an extension of the Kubernetes API in a Kubernetes native way. I think the best phrase to put it.
And okay, so let's dive deeper into this when we get to the implementation of the operator. But first, I would like to also look a bit at the different options to deploy Flink on Kubernetes, because it's potentially confusing because there are a few different options. So one is what is maybe called like standalone deployment, where you basically have a bunch of YAML files that define a job manager and task manager deployment. Then you have native Kubernetes mode, which is basically a bash script that runs some Java, and this will talk to Kubernetes to deploy Flink. And then there is the operator that we're talking about today. So what are the differences between these approaches, and when should you use which?
Well, it's again a good question, because it's a confusing, or can be a confusing topic for most of us. And before the Flink operator, we had these two distinct approach to deploy Kubernetes resources, the native and standalone. And we cannot really compare them to operator because the operator is a higher level concept. And actually under the hood, it uses both deployment modes as of today. The biggest difference between the native and the standalone mode that pre-existed in Flink is basically how you schedule the resources, how you talk to the Kubernetes operator. In a standalone mode, the Flink application is not aware that it's running in a containerized environment. It's not actively managing resources or talk to the Kubernetes API. Whereas in a native deployment mode, it's the Flink application, the job manager itself, who is responsible for managing resources, spinning up, turning down task managers on the fly. So this is, I think, the biggest difference between the two. And when we started developing the operator, first we supported the native integration because it has already a rich feature set that we wanted to have in the operator. And basically, by submitting the cluster, the native submitting a custom resource, the native integration took care quite a bunch of things already. So that was a nice thing. But later on, there were requests to support the standalone mode because the native being there in Flink, I guess from 1.12, 1.13-ish versions, and you couldn't deploy older versions, jobs with older versions before, and also having the Flink application itself controlling the resources. It has to have a service account and has some security implications in a deployment mode. In most of the cases, it is not a big concern because usually the operator is deployed in a dedicated namespace, and the managed resources are deployed into watch namespaces, and you only have to give a limited set of permissions for the Flink itself to spinning for managing pods and config maps, basically. And yeah, so, but still with both native and standalone mode, the lifecycle management, like upgrading a cluster, restoring the job from a save point was still a manual task that has to be carried out either manually by the human operator or has to be baked in some infrastructure component like CI/CD pipelines and whatnot. So we clearly needed a higher level of something that can do this automatically and takes care of these tasks automatically on behalf of a human operator. So basically the Flink operator supports everything we have in standalone and native mode, plus all the automation that is pretty convenient for managing jobs in production environment.
Okay, so we basically went already to talk about features of the operator as part of this question. So quickly going back to standalone versus native. So I want to stress one point that you mentioned, and that is that in native mode, you give the Flink job manager permissions to create pods and config maps in Kubernetes, which is probably a big deal in some environments because it means that, and you can execute arbitrary user code on the job manager. So in theory, a bad actor could access your Kubernetes pods and delete Kubernetes pods or start new pods with native mode. And that is not the case with standalone mode as far as I know. In standalone mode, we only give permission for creating config maps for the Flink high availability service.
Yeah, that is correct. Yeah, you're correct here.
And another benefit of the standalone mode is I think that the deployment time is a little bit faster because in standalone mode, we are scheduling the job manager pod and the task manager pods at the same time. Whereas in native mode, we first schedule the job manager pod, then it waits for the job graph to be generated, and then it requests and schedules the task manager pods.
Yeah, in certain cases, a restart would go faster. And when it comes to reactive scaling, for example, it's a better fit for standalone deployments, because like you have a fixed set of resources and job basically scales within that cluster boundaries. We could scale jobs by the operator themselves, but we have to shut down the task managers in this case, and that could take a longer time. You're correct.
But there are also, I would say, downsides that kind of come from this decoupled scheduling architecture. I mean, first thing that comes to my mind is like if you're using Flink on a session cluster, if you want to create a session cluster in the standalone mode, you have to kind of predefine and manually kind of manage the size of the session cluster because it's a fixed size. Whereas with the native integration, the native session clusters are elastic within a Kubernetes cluster. So if you're not running any jobs, it will not start any task managers. And as you start more and more jobs, the number of task managers will scale up or down. And I guess another problem that could happen with the standalone mode, which I don't know how common this is, but I think it's definitely a concern. If a task manager kind of becomes unavailable, like slows down to the point where Flink cannot really use it anymore, but Kubernetes still doesn't detect it as failed, you will not have enough resources in the cluster, because you have to ensure kind of externally that there are enough healthy task managers. But what is healthy from a Flink side doesn't necessarily translates very easily to what is healthy from a deployment or a stateful set standpoint in Kubernetes. So yeah, I think there are good use cases for both ends. I think from a very high level, the native integration should be the first choice for most users, just because of the simplicity of the model. If they don't have like strong concerns with the security implications, if it's not a problem in that particular user environment, or if they don't have very specific like scheduling requirements and custom setup, then I think the native integration provides a super simple way to run Flink on Kubernetes in general.
Yeah, I think another big takeaway is that the operator is able to run in both modes and is the preferred option for Flink on Kubernetes.
Yeah,
because it's conceptually the better approach to use an operator that is responsible for managing Flink clusters instead, because then you can also do things like upgrades, job submission, and so on through the operator instead of doing this manually. So then let's talk a little bit about features of the operator. So how do I do the basic operations, like submitting, like creating, let's say, a session cluster, submitting jobs to it, creating application clusters? Like, what does the API look like for a user?
So as we mentioned earlier, so the Flink Operator project defines basically two types of new custom resources, which are the extensions of the Kubernetes API. The two main resources that are introduced are the Flink deployment and Flink session job. Flink deployments represent Flink clusters, either a Flink session cluster, which can run multiple jobs, or a Flink application cluster that is dedicated to a single job, which is the most commonly used way of deploying a single job in production. And you have the Flink session job custom resource, which represents a single job that is to be run on an already existing session cluster. So the way users interact with the operator and to deploy these resources is that they create a simple YAML file with the specification of the custom resource. For Flink deployment resources, for cluster resources, this usually means a YAML description of the Flink, the Flink configuration that they want for that cluster, resource specifications for the job manager and task manager containers, and optionally a specification of the job itself for application clusters, which would contain the commonly known arguments like main class arguments, the main class itself, jar, URI, and those kind of settings. And once you created your YAML, you simply submit this to Kubernetes using the kubectl command line utility, or depending on your environment, however you want to submit resources to Kubernetes. And then the operator will take care of translating this to actions and deploy it to the cluster, deploy your cluster.
Yeah, it actually carried out by the concept of a control loop. So in a custom resource, you define the specification. This is the desired state, how you wanna your job to look like. And there is a status part that is maintained by the operator. So you define the desired state, and the operator will periodically try to bring up resources and update the state until the actual state of the job becomes the desired state. So that is the concept of a control loop, and this is a best practice, a pattern in Kubernetes world, and in the Flink operator we also following that.
Yeah, so you can kind of imagine the operator would actually execute the same actions that you as like a human operator would, given a cluster specification. So somebody else gives you a YAML that tells you how the cluster should look like, and the operator will then go in, set up the Flink configuration, submit the cluster in using the native or standalone mode, depending on what mode you selected in your YAML. And then it will check the cluster, make sure that the Flink job came up. If there was any problems that it can fix, then it will try to fix it. And it will basically just keep an eye on your cluster. The control loop is basically the operator periodically checking and making sure that the Flink cluster and Flink job still behaves according to your specification. And if something looks fishy, then the operator will try to fix it.
Yeah.
So is the status field the only thing that I get as a user to monitor the health of my cluster? Or is the operator also emitting events, for example?
You have both options. The status field, it's sort of an internal state of a custom resource. So, and it is mainly utilized by the operator. So we have technical statuses, the job status, and other thing that is used to safely maintain the custom resource, because it is important that the operator itself is stateless. It stores this actual state of a custom resource within the custom resource in the status field. So in case the operator goes down, comes back, there is no major impact of your running job. So that status field is basically a technical status. Users can dig into that, and it is a useful information for debugging purposes also. But for user-facing event and status update, we introduced a concept of having listeners in the operator when users can subscribe the changes and events that are emitted by the operator. So we are triggering two types of events that one part of the events is standard Kubernetes events. And if you look at the Kubernetes resource itself, you see those events listed. But beyond that, we also important status changes also that gives you like a more user-friendly way of determining the status of the deployment. So there you have like created state or deploying, running, or failed state that otherwise it's not an actual state that is stored in the custom resource. So these are the things that the operator can emit. And this listener mechanism, it's actually an extensible and a pluggable mechanism, allows the operator to easily integrate to control planes. So if you want to decouple the operator from the control plane, the operator can ingest events into a messaging system, and your control plane can subscribe those events automatically. So the control plane doesn't need to fetch and subscribe events and talk to the Kubernetes API at all to determine the status. So we try to give a solution that is extensible so that the operator itself can be integrated with various infrastructure components.
Yeah, and I think I just want to like reiterate on this like last point that Mátyás has mentioned. So like one of the key design philosophies of the operator is so that it's very flexible, and users should be able to integrate it in any kind of like internal Flink platforms or internal infrastructure. I mean, I think one of the like high level or kind of more ambitious goals of the operator is in the long run, like management of Flink jobs, like the pure management part, like upgrades and submission and stuff, should not be something that is like the secret sauce of some like arbitrary like Flink providers, but it should come from Flink itself. So because this is an integral part of any any Flink production platform, or anytime Flink like users like want to make upgrades, they face the same problems, and the operator is kind of aiming to solve this in a very robust way. But at the same time, we try to make it flexible so that you can actually make this like the core of your internal Flink platforms or your Flink offerings, and you can build on top of this, and you can add the nice features on top of this, but you don't have to deal with like these mundane tasks of stateful upgrades and whatnot.
Yeah, it's a very nice feature. It's pretty cool. So let's talk about upgrades, save points, and so on. So how do I do this with the API that you described?
Yeah, basically, when Gyula mentioned that we have two types of custom resources, the Flink deployments and the Flink session jobs that is monitored and managed by the operator. And when you change the specification of these custom resources, then the operator will detect the change, and it will pause your application and then resume it with a state if it's requested. So in the operator, there are three basic upgrade modes that we support: stateless, lost state, and save point. And when it comes to restoring the job, if it's a stateless upgrade mode, the operator will restore the job from an empty state, simply that is convenient for developing purposes and in QA environments. And we have the two production grade upgrade mode, the last state and the save point. And the biggest difference between the two is basically in save point upgrade mode, we'll stop the job with a save point. So we need a running job, a healthy job for that to be able to take a save point. it takes it could take a significant amount of time depending of your state and state backend, sometimes minutes. If you just want to give a fast upgrade, or you want to restart your job, you can go with the last state upgrade mode that records the checkpoint and the save points in the HA metadata. So Flink takes the information from HA metadata and restores the job based on that information, whereas in the save point upgrade mode, it takes a save point, records it in the status as the last save point, and then it restores the job from that state.
So you mentioned that for stopping with save point, you need a healthy job. So let's maybe talk about in general what you do, what your operator does when the job is unhealthy, and if there's anything to recover from an unhealthy job.
Yeah, so there are a bunch of corner cases, and probably Gyula is a better fit to address this because he was on it and it covered all the corner cases. So yeah, you want to take this, Gyula?
Yeah, sure. So, I mean, of course, the upgrade situation is kind of straightforward when you have something that is healthy and running. And if you think of how you would also do an upgrade, users probably, in most cases, simply trigger a save point, like a save point shutdown, and then they like submit the job from that save point. So this is what happens normally in the operator also when you use the save point upgrade mode. But yeah, as you also hinted at it, things get a bit trickier when the job is failing. So what does the operator do with failing jobs in general? So on a very high level, not so much, and not because this is a missing feature. It's because Flink itself comes with all the utilities or all the features that it needs to deal with failures in general. So when you submitted the Flink application and the application fails, the Flink cluster itself will recover itself, so kind of self-heal. The operator does not need to actively intervene with running clusters, and this is a very important thing about the operator, that the operator is not something that is constantly like manipulating the Flink job. It submits it, and as long as it's there, we rely on the built-in and already extremely robust failure recovery mechanisms of Flink itself. So if there is a failure, Flink will recover from the latest checkpoint without the operator ever needing any input. But of course, if you're at the point where you submitted a spec change, you want to trigger an upgrade, and the job is failing at that particular point in time, there are different scenarios that we need to be mindful. So it depends a little bit on the upgrade mode that you requested, because that's something that you define. You tell the operator, I want stateless upgrade mode. I want to throw away my state. Or you want a save point upgrade mode. You want a save point for some reason. Or you simply say last state. You don't really care if it's a save point or a checkpoint. Just recover from what was the latest. So in the stateless case, we don't really care whether the job is failing or not. The operator will just simply delete the cluster and it will create a new one. You don't want the state, so it's easy. Doesn't really matter what was before. What matters is what comes after. For save point, this is tricky because save points can naturally be only taken when the job is running. So if you think like how you would solve it, well, it's kind of tricky to solve. So from a human operator perspective, what you would probably do is, if the job is failing and you know that it's not going to recover, then you will probably just shut it down. You search in your checkpoint storage for the latest checkpoint and use that for recovery. So that's, I think, what most people normally do. And if you have this is like application upgrade logic scripted, then this is when things become a bit hairy on your deployment side. The way the operator solves this is quite similar. If you requested a safe point upgrade mode and safe pointing is not possible, we kind of fall back to the last state upgrade mode, which will be what I described, which would shut down the cluster and restart the job from the last checkpoint or safe point, whichever was the latest state available. And the mechanism for this is a bit different from what you would normally do. The operator doesn't have access to your checkpoint storage, or it cannot really look up checkpoints from your own system. But what it will do instead is it will rely on the checkpoint metadata saved as part of the high availability metadata that Flink already stores if you use the Kubernetes high availability integration. And we will simply leverage that information to start the job. So it's a very, very simple process. If you have high availability turned off, then you cannot use the last state upgrade mode, which means you can only use safe point if your job is running. If your job goes into like an unrecoverable restart loop, then you have a more sticky situation because the operator simply cannot like confidently tell what was the last checkpoint. So then you might have to do some manual intervention to tell the operator which checkpoint to use to continue from. This is not impossible to do, but I would say most people who run Flink on Kubernetes should probably use the Kubernetes high availability. It doesn't really come with any strong external dependencies. It uses Flink, it uses Kubernetes config maps. So it's a quite natural fit to use it together with the operator to get the most out of the system.
Yeah, so if you're not concerned about the security implications of this, it is highly recommended. The operator is just trying to make sure that the state is not lost and just trying to save the user in every possible way if the state would be corrupted, and instead it stops when it is not confident that it can restore the latest state. And then you need the manual recovery, which is a very rare occasion.
But also a simple process, yeah. So
the one thing I noticed in production is with the Kubernetes high availability mode is that you might run into a situation where the Kubernetes API server is overloaded because Flink is updating the config map on every checkpoint. And if you configure like a very high checkpointing frequency, and if you also configure more than one retained checkpoint, then this config map update can grow quite large, and it's very regular. And at some point, you might run into rate limits, for example, on Amazon EKS, which has rate limits on the API server. So this is something that I've seen in the real world happening with Flink.
Yeah, that was basically one of the reasons that we're trying to lift off the burden of sending events and status updates via the Kubernetes API and try to decouple the operator of the pure like technical side of the event. So at least the external system don't need to put extra pressure on the Kubernetes API. So it's basically the Flink operator itself that is using the Kubernetes API server, and this is more predictable. So
yeah, but I mean, you're right. If the Flink Kubernetes high availability itself cannot function properly because of this, and maybe you need to turn it off, then that will have implications to the operator. And I think there are some plans to also support other high availability like providers. Like I would say probably Zookeeper is the realistic alternative that has been the historically like most popular high availability store for Flink. yeah, but we don't have a good integration for that yet. There are certain tricks that we can play with the native Kubernetes HA, which makes it very convenient for us. Yeah, but I think in theory, nothing prevents us from eventually solving this for other HA meta stores also.
So I have another follow-up question regarding the last state upgrade mode. So are you really, let's say, fiddling with the data in the config maps to look up the location of the last checkpoint when you're not able to stop with a save point? Or are you just relying on the HA mode of Flink? So basically just killing the pods and restarting them, and you're relying on Flink to just recover from the last state?
Well, it's both a little bit. I mean, we're fiddling with it, but not to extract the checkpoint information. The checkpoint paths, unfortunately, are not directly exposed in this high availability like data. They're just pointers to the location where the checkpoint location is written. So it's a bit more complex, unfortunately. So we can't do that. So the only thing that we fiddle with actually is the job graph itself. So to be like very precise, what we do when you request a last state upgrade and you have HA enabled is that we delete the cluster resources, the deployments and the pods. That leaves the high availability metadata there. Then we delete the job graph information from the high availability metadata. This is very important so that when we submit the new cluster, Flink will regenerate the job graph, your pipeline, using your latest Docker and job image. But beyond this, forcing Flink to recreate the job graph using your latest information, we simply rely on the HA mechanism, which will, once the job comes up, automatically pick up the latest information from the checkpoint, so from the HA data. So it's technically a quite thin integration.
And the job graph is just a pointer in the config map that you're removing.
Exactly, yes.
Okay.
That's true.
Yeah. And is there an option to configure, let's say, a timeout for trying to create a save point? Because I think I agree that it's a good idea to try to stop a save point. If it doesn't work, fall back to last state. But I think there's a common case where a cluster just happens to be in just one restart, but then it will be healthy again. And it sounded like you would immediately fall back to last state. But I was wondering whether it would make sense to have something like a certain number of attempts, for example, and a timeout for doing a stop with save point operation instead of immediately falling to a last state.
Yeah. So currently there's no timeout mechanism. So by default, if the job is not running at the time when you try to make the upgrade, it will immediately fall back. And kind of the rationale is that when you want to take an action, you probably want to upgrade as soon as possible. I think that's a good idea, and we should definitely introduce something like this. On the other hand, at least we have an option to disable the fallback. So if you want to tell the operator that, please only use save point. If you cannot use save point, give an error or something like that, then what will actually happen is, if the job is in a restarting state, so not terminally failed, then it will keep retrying. But again, there's no timeout. Keep retrying. If the job terminally failed, so there's no hope for a successful save point, then the operator will actually emit an error so that the user can get an immediate feedback that it needs to intervene because there's no hope for actually executing this properly.
Yes.
And can you also create regular save points with the operator?
Yeah, So beyond these automatic save points, user can trigger save points themselves manually by just defining a save point trigger nonce and a field and just bumping the version of that. And the operator will take save points, and also they can set and instruct the operator to create or trigger save points periodically based on a time definition in the operator, and that can be like a general setting, and you can override it per custom resource for your job.
And how is the operator storing the information about the save point?
In the status field that we already mentioned. So the operator keeps track of the save point history, and also picks the latest save points for itself for restoring the job if needed, and also it disposes all save points based on account or time if requested. So it's a nice feature and a convenient feature, because usually user created save points are just piling up on your storage and never being taken care of. So the operator does that automatically if instructed.
But in principle, if I configure the thing so that I have always like 1,000 last save points, my status will have 1,000 save points.
Yes.
Yes.
Yeah. Okay. What about upgrades of Flink jobs? So if I have version A running of my job and now I change some things and now I want to do a stateful upgrade to version B, how do I do that with the operator?
Well, we discussed how it happens basically when Gyula was mentioning the upgrade modes. Basically, you define a new specification. The operator is subscribed to these changes, and when it detects the changes, it will restart the job using the new specification and the old state that is available. So
yeah. So by default, state is always carried forward. You as the user never need to worry, as long as you have the stateful upgrade mode set, save point or last state, you never have to worry about like taking save point, shutting down clusters, restoring from the correct things. This is all handled by the operator. So from a very like high level perspective, you submitted YAML 1 for version 1, and then you changed the Flink configuration in your YAML. You submit the same updated YAML again, and the operator will do its thing, and you will get the updated cluster.
So I change my jar file name, whatever, to the newer version, and then the operator will do the right thing, basically.
Maybe it's important to highlight it's not a delete and a create operation. For example, if you do this with kubectl or Helm, so you don't delete this custom resource, you update it or patch it with the kubectl apply, basically. So the custom resource will be there, and as soon as it is not deleted, the operator will consider it as a running job, even if it's in a suspended phase and no actual resource is running.
And do you also support rolling back upgrades?
I think this is an experimental feature at the moment. So we have a concept of the stable spec. So once the operator upgrades the cluster, initially this new specification is considered like unstable, and the operator will observe the job status, and when it sees it is running, this is the healthy condition that we have in the operator at the moment for a healthy job, then it marks this state as a stable state. If for a certain period it is not happening, the operator will roll back to the last stable state that we recorded in the custom resource. So making sure that the health of your operator will be restored.
And what features do you have for configuration management?
Yeah, so
Yeah, go ahead.
yeah, so configuration in the context of the operator happens on a few different layers. So you will have configuration for the operator itself. So you set this in like when you start the operator. You also have configuration, default configuration for the Flink resources that are deployed through this operator. And in each resource that you as a user deploy using the operator, you can override the default configs. So it's like kind of like a hierarchical Flink conf YAML. That's the way you can imagine this. So in terms of config management, so for the operator specific configs, they are stored in a config map on Kubernetes, and the operator will periodically refresh the configuration based on that config map. So if the user wants to change something, some configuration for the currently running operator, so the platform configuration, then you can simply update that config map, and most configs can actually be dynamically updated. So the operator will kind of refresh its configuration and reload it automatically. And for the user facing things that actually affect the Flink clusters, the user can just set them in their own resources. If they need to change the cluster configuration, that's basically an upgrade. But the operator, there are also certain configs that only affect how the operator handles the job and not the running job itself. So if the user only changes those configuration in newer operator versions, there will not be like a Flink cluster upgrade triggered. So the operator can actually differentiate between changes that require a restart of the Flink cluster and changes that only affect how the operator manages this resource, and that doesn't require a restart.
Yeah.
Is there also the option to define, let's say, global configurations for, let's say, a namespace or so that is picked up by all clusters created in this namespace?
There's only one kind of global default configuration for an operator. We don't have per namespace defaults. This is actually a very good question, because this is relevant not only for configuration, but also generally like specification. So I think in a very ideal world, you would like, if you build a platform, in many cases you want to provide like default like spec settings, and also default Flink configurations like metric configs and whatnot, maybe on a per namespace or a per whatever basis. So this is not something that is supported yet. You have to handle this on your like platform level. But I mean, it's on our radar, so to speak. We're still kind of thinking of what would be a right, like most generic way to support something like this that serves all that would serve the needs for different platforms.
Writing namespace specific configs or global configs, it's not a big deal, but adding templates that are namespace specific, it's challenging, because then you would only need to apply the differences based on a given template, and then we might need to change the CRD and whatnot to add it. So it's not an easy way to do.
And I guess you support auto-scaling by changing, let's say, the scale in the template only for standalone mode with like standalone deployments with reactive mode.
Actually, we support both, but in a standalone mode, if you change the parallelism, for example, we won't trigger a restart carried out by the operator. So we just scale the number of replicas, basically, and then it happens automatically. So we won't trigger an upgrade in this specific case. We cannot do this with the native mode. It requires a standalone mode.
Yeah, but autoscaling is actually an interesting topic for the operator, because the operator allows us to make autoscaling a bit more flexible and even support it for native mode, not in the reactive way how Mátyás described it, that it would work for the standalone, but on a more high level way. So so what you could do technically, like already today, is you could set up like a horizontal pod autoscaler for the custom resource, and the custom resource itself, the Flink deployment resources expose like a scale sub resource which Kubernetes needs to be able to use these autoscaling policies. So then you can set up like monitoring against the task manager pods, and then the autoscaler, the horizontal pod autoscaler would automatically change the specification of your Flink deployment. And then you kind of delegate the scaling process to the operator. And then if it uses standalone, then it will do one thing. If it uses native, then it will do another thing. But the point is that you can have auto-scaling for both native and standalone deployment modes through the operator. Even if one is less efficient than the other, it's still technically possible.
Yeah, that's quite nice. Yeah. Great. So to wrap up, I would like to ask or quickly talk about the implementation of the operator itself. So I think the operator is implemented in Java. Have you considered implementing it in Go as well?
Yes, we did, since, you know, Go is the obvious choice when it comes to building Kubernetes native applications, and with its resource efficiency, it's an attractive selling point. And we also, as Gyula mentioned, tried out a couple of open source operators that are written in Go, and we basically felt that we are missing quite a bit of integration with the Flink itself. For example, being able to use the Flink client for submitting jobs and interacting with the cluster was an attractive thing that otherwise you would lose if you go with Go. And also, like the metric system that exists in the operator also is just an extension on top of the Flink metric system. So and a bunch of other things where we could leverage of having a Java based solution for that. And yeah, I think I've been doing some research and trying to find something similar, like a framework that we have in Go for building operators, like the KubeBuilder or the Operator SDK. And luckily, I found a promising project. It is called the Java Operator SDK that has the same concepts, the same abstractions, similar to the KubeBuilder or the Operator SDK. It provides framework where you can only focusing on actually the core logic, the business logic on the operator, and the rest, the handling the events and talking to the Kubernetes API server, all the retry mechanism, all the details are hidden away from you. And we evaluated it, and we had very positive experience, and we advanced pretty fast writing the operator in Java. And so far, we haven't had any issues, like any blocker issues with the Java operator SDK. So based on experience and also the Java experience, the wealth that we have within the Flink community was a strong selling point to pick Java instead of Go. And since the operator is a long-running process itself, there was no real benefit of going with Go, even though that's the latest greatest. I think with the Fabricate client that is used in the Java Operator SDK, and all the integration points finally convinced us to go with Java.
Yeah, and I think if we would have written it in Go, I think it would not feel as like an integral part of the Flink project, because I mean it would look very differently, but still would kind of do the same things that Flink does. It would still have to use the clients and everything, but in a kind of like a different way than how it is like used in the Flink project itself. I think with the Java Operator SDK, and with the metric system integration, and basically this allows us to integrate with everything that Flink provides. Many of these things are not like very generic APIs, they're Java clients, and you have to take what you get. So I think this is it was a very good decision, and it's a very convenient way of integrating it. And as Mátyás said, the Java Operator SDK is just a layer on top of the Fabricate Kubernetes clients, which is also used by Flink itself. So the core Flink and the operator share the same core client integration to Kubernetes. This further kind of reinforces this decision, because we are using the same kind of like battle-tested Kubernetes integration. If it works for one, it will probably work for the other, and vice versa.
Cool. And do you have any data on the, let's say, adoption and usage of the operator, and also general feedback from the users?
Yeah. Not at the moment. I mean, we haven't put anything on the documentation that the operator itself is being used in production by this and that company, but based on the feedback on the support channels, it is quite obvious that it is being evaluated and being used by the biggest and heaviest Flink users all over the world. And most of the questions are around, at least for the initial step, how do I migrate? How do I integrate? How do I use? And we have those quite a bunch. So I guess the popularity of the Flink operator is growing, but giving you any exact numbers for this, I think it's impossible.
Yeah, we don't want to name names, but I think it is already used in production at quite a few companies, and some of them. I mean, there is like surprisingly good traction on this, even like initially, and as Mátyás said, so far the experience of the users have been very good. Of course, we like found a number of issues that we fixed, but even in our own experience, we have been using this actively in different environments and different contexts for several months. We really have good feelings about this.
Yeah, we work together for adding larger features with companies. So the Flink session jobs was the contribution mainly for one company, and the standard deployment is another larger company. So, and it is basically the two of us who is continuously maintaining and actively maintaining a project, and companies just by defining a flip usually change and extend the feature set of the Kubernetes API, but we keep maintaining it.
So what's coming next? What's the roadmap for the operator?
Good question. You want to predict, Gyula?
Yeah. So currently we're on release 1.10 or something like that. But the next, we're planning to release the 1.2.0 release in the beginning of October. That will it will be a major new release. It will introduce the standalone mode support and a bunch of other things like health probes for the operator itself, and some improvements to the event and metric system. So it's always worth upgrading to the latest one for people who are already using it. Beyond this, it's a bit tricky to say. I mean, from our perspective, for at least the core feature set, the operator is more or less feature complete. So of course we have a lot of improvements on mind, but nothing groundbreaking, and I think that's a good thing. I mean, the operator project is not aiming to like kind of conquer the world and add all the features that you can imagine in a Flink platform. We're aiming to kind of keep the feature set slim to a reasonable extent and kind of make sure that it's the core is nice and robust. Yeah, but maybe some things that we know that we have to improve would be the rollback mechanism, kind of adding more flexible ways for users to define health conditions for Flink jobs. So maybe running is not it's not a super robust health metrics. Maybe you want like successful checkpoints or stuff like that.
Two specific questions came up on the support channel. So one is to use the stateful set instead of deployments.
Yeah, for standalone.
Yeah, that one, and the other one was basically the A/B testing. But as Gyula said, we are not sure if it's a good fit for the operator or it has to be implemented outside operator with integration. So yeah, we'll see. If there's a strong need, we can add those, but otherwise it would probably be a better fit in control and even to scaling itself.
Yeah, and we also have some features in mind that kind of would aid Flink in like recovering some errors that are currently not recoverable by Flink itself. So there are some cases when, for instance, you get a restart loop and your job restarts 1,000 times, and there is maybe a slow like class loader leak and the task manager meta spaces are full. Then even Flink like restarting the job itself will not solve anything because it crashes on itself. And maybe in those cases, it would be nice to trigger an external restart and not only rely on Flink's internal mechanism. I think these are good candidates for the operator. It will make the operational experience more robust. Yeah, but these are the things. And of course, we are always looking for feedback from the users and any pain points that we discover along the way. We're happy to fix.
Great, perfect. So I'm done with my questions. Do you have anything else you would like to mention as part of this interview?
I think we covered quite a bunch of topics, sometimes even in detail, so I don't have any. You?
Yeah, maybe about like the contributions. The Kubernetes operator is part of the Flink project, so anybody who is interested and already contributing to Flink can, in a very similar way, contribute to the operator. We use the same general process of like how the Flink project works. You open Jira tickets, discussions on the mailing list, flips, PRs. So it's everybody is welcome to join in this effort. It's quite tractable at this point. It's not a huge project yet, so I think it's a good place to start for new Flink contributors also.
Yeah, and it's pretty easy to work on the operator itself. You can run it in your local minikube. You can even run it in your IDE, your favorite IDE. You can debug this, and it's pretty easy to add any new features or fixing any bugs. So it's good for everyone who is new to Flink or wanna go deep dive into Kubernetes integration.
Great. Yeah, I really enjoyed the conversation. I think I learned a lot about the operator today and how it's implemented and all the features it supports. And thank you both for joining this interview and working on the operator. Keep up the work, and see you soon for another interview.
Yeah,
Thanks.
Thank you very much.
Thanks. Bye.
Bye.